Good morning, everyone. It's a great pleasure for me to introduce Professor Elena. I met Elena the first time actually in Zurich in 2014, and she was giving a great colloquium on the thick disk and thick disk formation, and I was nearly turned into a Redshift 0 observer. But luckily the proposals were never accepted, so I stayed at Redshift 2. But in any case, Elena started her career in Italy, and she did her doctorate degree at the University of Milan, where and then she moved north to Munich. She was a research fellow at MIT. Before then, she received the Marie Curie Fellowship for the University of Zurich, and before actually moving here to the ITC, where she was a CAC Foundation Fellow, and before then joining the faculty at the University of Wisconsin-Madison in 2012, where she's now an associate professor. Her research, as I think most of us know, has mainly to do with analytical and numerical models of the stars within our Milky Way, but she has also done research on the dark matter halo of the Milky Way, as well as the dwarf spheroidal galaxies. And so today she will be talking to us about the Hercules stream, stars visiting the solar vicinity.
Thank you very much, Sandro, for this nice presentation. And thanks, of course, to the ITC for inviting me to give here the colloquium and to have me back here for my sabbatical. It's always a joy to be back and see so many faces I know and coming to my talk. So for me, this is really exciting. And I want to show you preliminary results, actually. This work is not published yet, but I want to engage you on the work I'm doing right now, because I think galactic dynamics is really, going through a renaissance right now, and so I want to tell you what I feel are the very hot topic for that could be explored with Gaia. So let me also thank my collaborator, which is Alfonso Aguirre at the Institute of Astronomy in Tenerife. So this work is in collaboration with him, and he started actually the Gaia Sprint meeting in New York, where right after the beautiful data from Gaia came out, and they really captured my attention for the solar vicinity. So a few words about why Gaia is so interesting. Not only Gaia, but all the missions about the Milky Way are really important, because the Milky Way is becoming the subject of the great observational efforts of all these telescopes and missions in the last few years. And this decade, really, we will learn a lot about the Milky Way disk, the halo. And what we want to learn, not only from the Gaia data, but also from other surveys like Gala for the chemical abundances, Apogee for the SLOAM 4, and the SLOAM 5, which is actually coming up in the next few years, taking more and more chemical abundances for many elements, for many stars, for hundreds of thousands of stars. Gaia is giving us proper motion and distances for 1.7 billion stars, in the Milky Way. Already the Gaia DR2 release gave us information about proper motion and parallaxes for more than 3 million stars in the solar vicinity, from 200 parsec up to 1.5 kiloparsec. So of course, what the community wants to learn about Gaia, well, we would like to have some insights eventually about that matter. That's always, something we want to learn about. But we also want to understand maybe better for our galaxy with this detailed data, more about, the spiral structure, which we know that the Milky Way has, but it's still very debated, the nature. And we have here Artur, who actually studied for a long time the spiral activity in galaxies. We also want to know the relation to the bar. There's a stellar bar which seems to be very intense, very strong in the Milky Way, and also to the bulge, and the nature of the bulge. And also we want to, in general, try to understand better what the accretion history of the Milky Way, with all these satellites coming in, the globular clusters, how the halo is accreted. And I think we are really now at the time when we finally can open our eyes into the Milky Way. So why the solar neighborhood is so interesting? So this is actually a view of the DR2 Gaia data, that the second release that came out on 25th of April of this year. So this is actually is showing us in the plot. This is the solar vicinity. So these are 300,000 stars within 200 parsec from the sun. And those are the stars for which we know now the azimuthal velocity from the data and the radial velocity too. So for these stars, as you can see, the distribution in the velocity space is actually not smooth. This was already known since Hipparchus, but Gaia is really revealing actually presence of shells and also arches. So the stars do have, they seem to accumulate in overdense regions, elongated. And so these overdense regions are actually called moving groups. So this idea of moving groups, I believe, came from Egan, and it was in 1958. But so he realized that there were stars with coherent velocities, and he called these stars moving groups. But he believed that at the time that those stars were formed, they were actually the formation of open clusters. So they were actually formed, in dense regions and then evolving. And of course, the idea now is trying to understand what is the origin of these, out of equilibrium phenomena that we see in the solar vicinity. So basically, Gaia, if there's one reason why it's so interesting, it's because it's revealing us right now a big quantity of time-varying phenomena, time potential varying phenomena. And we see an expression here, just in the solar vicinity. And I think for this reason, with the depth of the data and the quality of the data that Gaia is revealing us, I think it's time for theorists to also try to understand what's going on, especially in the disk and in the solar vicinity. So among the moving groups, let's say the most studied so far is the most prominent, which is, you see these stripes here, Hercules. So Hercules has, as you can see in the velocity space, it's slower. So the sun is here. Let me tell you where the sun is. The sun is more or less here. So it's basically in the main mode of the motion of the stars in the solar vicinity. And Hercules seems to be a group of stars that are slower than the sun and also moving outwards. You can see better maybe here in the UV plot. So here the velocity are actually in the local standard of rest. So so U is pointing towards the galactic center, V is towards the rotational velocity, and the sun is more or less here, not exactly at the center, 0, 0, but slightly moved from there in the mainstream. And these groups here, these circles, are actually the overdense regions that are very well defined now in the Gaia DR2 data. And this is Hercules. It's the same as here. So Hercules is actually moving outwards because it's in negative U, and V, so it's moving outwards with respect to the sun. And there is a gap here between the main mode and these groups of stars. So these are, all moving groups that have been identified, as I said before, with Hipparchus, but now we're just the quality of the data is so amazing that we can see not only overdense regions, but even elongated structure around them. And of course, they are still, there's very hot topic right now to understand what's going on. So what is the origin of this Hercules stream or moving group? Well, as I said, the stars have a small angular momentum. They're moving outwards with respect to the sun. Actually, the orbit seems to be quite eccentric, so they're not circular as the sun. And also, when people have tried to look at the stellar ages in the last decade and the chemistry, so the abundances, it seems that they don't have a common age or a common metallicity. So this brought to the idea that these moving groups are actually not formed in an open cluster which is actually disrupted, maybe like Egan was thinking about, but they might be actually signature of dynamical phenomena that are happening into the disk. So we know that this is a view, so it's adapted from Mameni 2006, it's in the annual review from Just Blend Autumn and Orpin Gerhard. So this is maybe an artistic view of how the Milky Way might look like. So I would be curious to know from Mark here if he agrees with this. But anyway, just to give you, an insight on the fact that we know that there is a bar. The bar is with respect to the sun. This is like the disk seen face on. So the bar is actually inclined almost between 28 and 33 degrees with respect to the sun. We also have spiral structures that we know are in the Milky Way, There's still a debate, how many arms there are. So we know that there are features, like a spiral structure and a strong bar, and how this feature can affect actually the moving groups that we see in the solar vicinity. This is actually the question. So for a stellar bar, there are three strong resonances, and not only for the bar, but let me start with the bar. So one is the corotation resonance, which is characterized by an orbit of stars moving at the same azimuthal frequency as the perturbation, so as the bar. The inner Lindbland resonance and the outer Lindbland resonance are instead characterized by two radial oscillations, so for every azimuthal oscillation in the frame rotating with the bar pattern speed, the bar pattern. But there are additional resonances, the inner ultraharmonics and the outer ultraharmonics, which are in between the corotation and the inner and the outer Lindbland resonances, and they're characterized by four radial oscillations for every azimuthal oscillation in the frame rotating with the bar pattern. So why resonances are important? Because the leading theories about the formation of the Hercules stream since the Parcos data, so more than 20 years ago, was exactly claiming that the outer Lindbland resonance in the Milky Way is actually causing those moving group of stars called Hercules. And this comes back to basically Walter Dehnen. So I'm putting here again the data, the beautiful data from Gaia. He used the data from Hipparchus at that time. However, his models, so he modeled the Milky Way with the old properties, the properties at the time that were known for the disk, and so it turns out that the bar was known to be around 3 kiloparsec. And depending, depending on the rotation curve and depending on the length of the bar, and depending on the pattern speed of the bar and the number of arms, so the resonances will change their location in the disk. So for that model at that time, here is the sun, and these are the outer Lindbland resonances. These are the orbits for stars at the outer Lindbland resonances. So the outer Lindbland resonances would be actually inside, with respect to the center of the galaxy, they will be more internal than the sun. For this reason, Dehnen thought that stars can be scattered at the outer Lindbland resonance and reaching the solar vicinity, because the outer Lindbland resonance would be inside with respect to the sun and the rotation, the center of the rotation. However, this picture is challenged now, essentially because of the new data about the bar. So from the VVV mission, VVV survey, and from the GLIMPS survey, actually also in Wisconsin, either Bob Benjamin in Wisconsin, either Ortinger with Weg et al. In this paper, they're actually claiming that the bar is much more longer and stronger than what was supposed before. So it's not 3 kiloparsec, but it's around 5 kiloparsec, because this matches the vertical surface density of the data. They are actually available now to the community. So they're claiming that there are strong claims actually that the bar is actually much, it is actually longer, but it also has a slower pattern speed that was thought before. So in the Dehnen model, basically the Dehnen model can reproduce the Hercules stream, so you can reproduce this gap here with the moving group, with the velocity that we observe, only if you have a fast rotating bar. That means that the pattern speed is around this value here, and if and if the bar is around the 3 kiloparsec. But when you start having a 5 kiloparsec bar, then, as I will show you now, the resonances actually are on different locations, and things become more complicated. So there's another possibility that appeared this year in explaining the Hercules stream, which is actually the bar corotation. So another resonance now, the corotation of the bar. So the idea here is these models are just semi-analytics, so they don't have they don't have a self-consistent and body simulation. However, so they have a static potential actually, and the idea here is that if you have a bar, so this is the bar, and this is the face on disk, and these are we are here in the rest frame of the bar, so we can see the orbits. The idea here is that if you go back to the data, and these data were before the DR2, so it's still coming from the purpose, the older data. However, here it's basically where it's located in the UV plot. It's Hercules here. So they're showing that the origin of the stars here are coming from the corotation of the bar. The corotation of the bar is actually this part here, these dotted points here, and these are the two Lagrangian points, the two stable points that a bar has, the two Lagrangian, in the raster frame of the bar. And so the stars that are coming to Hercules are all these different kind of orbits. A banana orbit, librating around the Lagrangian point, and these other orbits out the other Lagrangian point. So they are all reaching, the solar neighborhood, the solar vicinity. However, they talk about, stars are coming really from the corotation of the bar. Other theories, I'm just telling you all the possibilities that have been explored so far. Again, with the semi-analytic models. So the idea is, well, we also have not only have a bar, we also have spiral arms. So in this old work, actually Antoja explored the possibility that spiral arms could also create the Hercules stream. But as you can see here, they can, if they only have spiral arms, they can generate a gap in velocity. But if you look at the radial velocity here, is around 0, so it's not in agreement with the data that we know about Hercules. So spiral arms just themselves, they don't seem to be eventually so interesting to create the Hercules stream. What about spiral arms plus a bar? Again, semi-analytic models where the potential is again static and it's introduced by hand. So there are many papers that came out this year also. So here are some of them. So they all agree that you can create the Hercules stream, but the best match is always with a fast rotating bar. So it's not with a slow rotating bar. So sure, a combination of a bar and spiral arms can get a better match, but still, with a higher pattern speed. So there are some attempts now with a lower pattern speed, but people haven't converged yet to any consensus. So what is the goal of this work? Well, the idea is to have a model which maybe departs from being semi-analytic, maybe using self-consistent high-resolution and-body simulations, where the potential is not static, so can changing all the time. It can help us in understanding this time-varying phenomena that we see around the solar vicinity. So first of all, we want to, of course, the idea here, what I'm presenting you today is what we are learning about what the Hercules stream could origin in these models. So the first thing is to generate a model that has of a Milky Way, tailored to the Milky Way, in order to produce a slow, long bar with a pattern speed in agreement with the data that are now available to the community. And of course, to identify where the resonances are, corotation, the inner and outer Lindbland resonance in this model, the inner and outer ultraharmonics, the spiral arms, and see which are the features and what causes actually. Because the idea so far is that it might be a resonance, really. These might be stars, resonant stars. They are coming from a real resonance, or they are scattered from some resonances. But which one? And also, it would be ideal to identify signatures or in the kinematics that we can identify in the DR2 data to prove or to confute or to this theory. Okay, the methodology. As I told you, so if you know my work, you know that I like to try to use embodied simulations as a lab for testing ideas. So I usually my simulations are not immediately applicable to to comparison with the data. I have the philosophy to try to use them more, like an experiment, like an observational experiment in the lab, and then trying to understand the physics behind it. So they are quite idealized. Okay, so they don't have all the ingredients, but I try to get there the ingredients that I need to solve a specific problem, to tackle a problem. So in this case, for now, this simulation doesn't have the gas, and we will see that this might be actually a limitation. But it has a stellar disk to start with, and a bulge to start with. It's not cosmological, it's just in isolation, and it has many of the properties that matches the Milky Way observed today, according to the annual review from Lindbland author and Artvin Gerard. So the initial setup, so the simulation is called Galactic, which is the ancient Greek name for Milky Way. It hasn't been taken from other simulations, so I thought it was the only one left. So the initial setup for the Milky Way is the following. So this is the initial halo. So this is a Hercules profile. I always set up Hercules. It's actually at equilibrium. In the inner parts, it's very similar to an FW. So this is the bulge. In the initial setup, this is the disk, the stellar disk. As you can see, the sun in my simulations will be set up around 8.2 kiloparsec, so it's still dominating, so it's come more or less here. So this is the total baryonic mass stars of the disk plus the bulge. It's the green line here. So if you see at 8.2 kiloparsecs, actually it's still dominated from the baryons. And this is the total rotation curve, which matches, I would say, between 4 kiloparsec and 8 kiloparsec. It's matching pretty well the software data. And these are actually the range in radius where I think we can believe best the data about the rotation curve of the Milky Way. So it's more or less flat in the range of radii. In the inner parts here, there's the data we suggest, I don't know if they are really reliable, the data we suggest, a bulge and a bar pretty strong. So this is in the initial conditions before the bar is formed, so we have a better match later on this. Of course, I cannot say one word about the Q parameter. Alan is here. So the simulation is initially at equilibrium. So because the Q parameter is always, it's actually around 1.5 for this galaxy. So it has to be larger than 1. The structural parameters of the simulated galaxy, so the mass of the bulge is 8 times 10 to the 9, is within a factor of 2 within the data, the error bars, so it's pretty much in agreement. The Milky Way disk is also pretty much in agreement. If you look at the review from Lindbland author, we are absolutely within the error bars in matching the mass of the bulge and the disk. The dark matter is assumed to be 10 to the 12 solar masses, and the scale length, it's around 2.67 kiloparsec for the disk, and the virial radius is around 163 kiloparsec. The sun is chosen in these models to match the data around 8.2 kiloparsec, and this is a simulation with in total 90 million particles. So with respect to the simulations I've done in the past, I'm using now also an alive halo, which is actually very important, especially for the development of the bar and the interactions between the halo and the bar. So it's basically not possible to use a static potential for these simulations.
Elena, the halo is spherical, right?
Yes.
What do we know about our halo? Is it flattened in any way?
It's very debated. So
very much debated, okay.
It's one of the things we would like to know. I think at the moment people would debate, it's probably not completely spherical, which radius starts to be triaxial. I would say that for this specific work, maybe I don't have to right now be so worried about if the halo deviates from being spherical, because these are in the inner parts. So you're expecting that the gas actually, make a more spherical halo in the inner parts. So
it's not so much the halo, but the satellite like Sagittarius that passed near the disk.
Yes, this is another. I absolutely agree with you. We know we all worked on papers that are also considering the perturbations from Sagittarius. This model is idealized and simplified in that sense. So for now, there's no Sagittarius, there are no satellites. This is only considering the features inside the disk. But of course, And the next step would be, for example, introducing Sagittarius and see how all these resonances and features are going to change in the disk. So this is the first step solution. Okay, let me show you how this galaxy looks like. So initially, this will follow the evolution of the first 3 gigayears. So initially we form arms, and then after some times, more or less 1 gigayear, we start forming actually the bar in the inner parts. This is in the polar coordinates. This is in the Cartesian coordinates. I'm sorry you can see here, but this is around. So this is from here to here, from the center, galactic center here is around 20 kiloparsec on each side. And this is, so you can see here, this is the bar already formed. And you see after almost 3 gigayears, where we will stop this for now the simulation, it's more or less around 5 kiloparsec, which is actually a long bar. So what we need to learn now about this simulation, we need to learn, first of all, the path and speed of the different features. We form spiral arms, we form actually a bar. Path and speed, first of all, to see if they are more or less in agreement with the data, because we want to have a slow bar now and not too fast rotating. And this is exactly the way to do that. So what we did here is a spectral analysis. So these are the path and speed of all the features. So you can see here that is a function of the radius. So this very strong signal here is actually the bar. This is the bar for an n equal 2. We know that n equal 2 is actually the main mode of bar. You can see still the bar in n equal 4 again here. And if you, I don't know if you can read the number here, but the path and speed are around 35, 37 kilometer per second per kiloparsec. So it's an excellent agreement with actually the data within the error bars. But then we see other features. Of course, there are spiral arms. You can see here. These are the spiral arms associated with the bar. The bar drives also spiral arm formation. We also see patterns here in n equal 4 for arms. We've seen some of the 4 arms evolving in the simulation. They have lower path and speed than the bar, and they propagate, you see, much further out. So these are path and speed. Actually, this is the Fourier transform analysis of the surface density convolved in time. So these are path and speed computed every 2 orbital periods, 2 galactic years, so around 500 million years. But if you follow them, if you do them in other windows of time, you will see that the path and speed actually change. So the bar will slow down. So, because we exchange angular momentum outwards. So for now, this is the time, 2 gigayears, where more or less we have all the agreement with the observational data. That's what I choose now as the current time for our Milky Way. One thing to immediately say about all these plots, so this solid line here is for an n equal 2, that should describe very well the bar. This is the corotation resonance, and you see the bar intersects the corotation more or less at 6.8 kiloparsec. So that's where the corotation is, 6.8 kiloparsec more in our simulation. The other lines here, so this dotted line here is actually the outer Lindbland resonance, and this is the inner Lindbland resonance. And so you can see with the bar, so you can intersect here with the inner Lindbland resonance is actually inside the bulge now, so it's very, very internal in this model. The outer Lindbland resonance, you can see already that it's more or less, you can see maybe even better here in n equal 4, so it's around more than 11 kiloparsec away from the galactic center. So the sun is 8.2 in this simulation, so the outer Lindbland resonance is actually much outside the sun, very far away. So it's difficult now to believe that, these just if you look at the location of the new resonances, that the Hercules can come actually from the outer Lindbland resonance, too farther out from the sun. Other interesting thing are that the sun is also in the middle of almost nothing. So, except, there are no other resonances. The inner and the outer Lindbland resonances for the bar are around 5 kiloparsec for the bar, and the outer Lindbland resonance is around 9 kiloparsec. So, and if you look at the spiral arms, this is also very interesting. If you look at the spiral arms here, there are patterns around 22 kilometers per second per kiloparsec. So the corotation of the spiral arms is actually much further out, 11 kiloparsec. Again, much further out than the sun. And if you look at, and if you go to lower pattern speed for spiral arms, so if you get other pattern speed like here, there, or like here, for example, those around 10 kilometers per second per kiloparsec, they extend too farther out to have any interest, and then they are not so strong. The bar really stands out here in this model. So let me tell you what so how we can select now the solar vicinity. So this is the bar that we generate. So you can see also that's actually buckling. You can see this vertical shape here, like an X shape, which is actually also kind of in agreement with the data. And we have chosen the sun, which is more or less 28 degrees from the bar orientation, which is more or less between 28 and 33 is what the data would suggest. So I think we are pretty much in agreement. So, and this is the opposite. This is just an opposite patch with respect to the sun. I will show you later why it's interesting in this analysis. So how now we have a solar vicinity. So what we selected is actually looking like in Gaia, selecting in 200 parsec from the sun location where we're choosing to be the sun. Also, I have to say in our simulation, the sun is also in the middle of anything, so it's not on a spiral arm, so it's more or less in agreement what we know about. And this is these are now in the UV plot. It's the solar vicinity. So the sun would be located here, and these are all the stars. It's a view of a sample of the stars in the solar vicinity in the simulation. And you can see here that first of all we generate a gap which is more or less at the same velocity as the data, and we have overdense regions here in the same region where more or less we would identify Hercules in the data. So now that's promising. Of course, what is becoming now very interesting is to complement the analysis in the data, not only in the simulations at this point, using not only the velocity space, but also using the angle action space. Because we know that the energy, the angular momentum are the classical integrals for in-plane motion. In an asymmetric disk, there are, however, alternative set of integrals which are actually the actions. So we can define the radial action, and we can define the azimuthal action, which is actually the angular momentum of a star. And then, of course, there's also a vertical action, which is, because of the in-plane motion, the vertical motion are decoupled from the in-plane motions. We don't have to immediately think about it. So, of course, just to give you a brief, insight on this, there's also the angles associated to the actions. The angles, the radial and the azimuthal, they also, they are related. Their variation in time, so their rate, it's related to the radial frequency and the azimuthal frequency. And the frequencies are very important because I will show you later. They can tell us about resonances a lot. There are linear relations that I believe have been studied from Kalnisch and Lindbland about linear relations that would work between frequencies of stars if they are in resonance with a bar or spiral arms. Okay, what the data tells us about actions and the UV plot and what the simulations would tell us about. So this is again a view from a work from Wilmatrick et al. In 2018 and Walter Ricks. So this is again the UV plot I showed you before with all the moving groups, and Hercules is here. And this is the same data, the DR2 data, put in action space. So this is the square root of the radial action, which is related to the radial frequencies of the stars. So it tells us more or less a proxy for the eccentricity of the stars. And this is the angular momentum, which is actually normalized to the sun. So the sun is at 1. So here, so the importance of this work is that she could identify, they could identify the authors, these moving groups in the UV plot in the action space. So they are also look like overdense regions in the action space. And the action space tells us something interesting that the UV plot immediately doesn't tell us about. For example, the Hercules stream, which are these two plots here, is actually quite eccentric. So it doesn't have the eccentricity of the sun, 0. And also it tells us that this edge here of the plot are the stars, really this part here, are the stars that have the apocenter in the solar vicinity. So those stars are the ones coming from the inner part of the galaxy. So it's telling us that Hercules, just the data, it's now coming from the outer part of the galaxy. Now, if the outer Lindbland resonance is outside the sun, it cannot become from the outer Lindbland resonance, which is actually the accepted, since now it's the most popular scenario. So it's telling us it's coming from the inner part of the galaxy. These are the moving groups. For the moment, I haven't explored them, but in the data, we have, for example, this part here, these stars here, are the ones that have, the pericenter of the solar vicinity. So they're basically coming from the out part of the disk. And the asymmetry that you can see in the data is due to the fact that we have more stars coming from the inner part, the inner part of the galaxy towards the sun, than stars that are coming from the outer part of the disk towards the sun. So how they look like in the simulation? So I exactly did the same analysis and exactly tailoring to the potential of my Milky Way of this work here, of the data. So this is the UV plot, and now you see I can also identify, basically this part here are these overdense regions here, which are more or less in agreement, qualitatively with the Hercules stream. So, as I said, what does it tell us about the action? To me, what I learned most of it is that the stars are coming from the inner part of the galaxy of Hercules. That's what we should focus on, and they are quite eccentric because their radial action is actually not 0. Okay, let me show you where do they come from. So what I did next was to take the patch I selected as the solar vicinity, that patch of stars, and to select to identify the stars that today are, this Hercules stream in my simulation, and trace them back for the last 0.5 gigayears and see where they come from. So you will see now a movie where the black points will be these Hercules stars 0.5 gigayears ago and how they evolved towards the time of today. And you will see in the polar coordinates and in Cartesian coordinates where do they go. And all is in the rest frame of the bar, so the bar is always basically static. Okay, here is the bar. So these are the stars. So these inner points here are the inner ultraharmonics of the bar. The red points here are actually the corotation of the bar, and these blue points here are the solar vicinity. So basically, is the where the sun would be in the rest frame of the bar. And again, here is the inner ultraharmonics, the corotation, and the solar vicinity. So where do they go? So you can see the stars are actually librating around the Lagrangian. There are two Lagrangian points here. One is here and the other one is here. So those stars in the solar vicinity are actually librating around the Lagrangian point of the bar. They are reaching the inner ultraharmonics and coming to the solar vicinity. But if you look at, I don't know if you can see, by eyes also, if you follow just one point, you will see that their orbits are actually not closed as they should be in resonance, but they are loops. So that's also an interesting thing we noticed. And you see they move back and forth. They're kind of trapped around the Lagrangian point, but they librate around it, forming like a sort of V shape. Okay, so what does it mean? So what are we expecting at the different resonances? So this is a diagram that I believe it's called the Lindbland diagram, but it's in one of the paper of Jerry Sandwood, and it's very interesting. To me, it was very insightful to understand what I should expect at different resonances. So this is the classical energy angular momentum plot, and so these are the stars. So these are the stars that move on circular orbits. So at the corotation of a bar, or even with the spiral arcs, the stars exchange angular momentum and energy, but they keep their circular orbit. So they simply move in this direction. Depending if they acquire angular momentum, they move outward. If they gain angular momentum, they move outward. If they lose angular momentum, they will be inside. So this is not the case if you are in resonances like the inner and the outer limbal resonances, or even if you are the inner or the outer ultraharmonics. So in this case, you always exchange angular momentum and energy, but part of the energy goes in random energy, so the eccentricity is not actually kept. So the stars start losing their circular orbits and they become more eccentric. Now, in the action space, this is actually very well illustrated here. At the corotation with the bar, we should expect the stars not getting eccentric, but keeping their circular orbit, at least in this diagram, because they just should move horizontally in the action, in the radial action. So they just move like this. Whereas in the inner limbal resonance, they should be trapped. They accumulate, they accumulated here. They basically get trapped here, and the outer limbal resonance, they can move it outward. So, and the same would happen again for the inner ultraharmonics, similar to the inner limbal resonances, and the outer ultraharmonics more similar to the outer limbal resonances. What was very interesting for me here is that it's very difficult for stars that are trapped at the inner limbal resonance or the inner ultraharmonics to actually reach the solar vicinity. But what we saw is that the stars are actually achieving the inner ultraharmonics and then reaching the sun after, librating around the Lagrangian point. So what's going on? They need to have a process by which they gain angular momentum. And the corotation in itself, they cannot become eccentric because the corotation, they exchange angular momentum and energy, but they move like this in the action space. So they don't really, so the fact that the radial action is not zero for those stars tells us that the corotation has a role, but there's something else that gave some, so why these stars gain some angular momentum. So let me tell you what I think it's going on, and of course these need to be proven. There are in galaxies, in bar galaxies, it's interesting because you can even compute what is the angular momentum, the instantaneous change of angular momentum, some way the torques. And that's what has been done in this simulation. They computed here in a bar galaxy, they computed the torques. The torques that the bar can actually exert on the stars. Now it turns out that if stars are not ahead, but behind the bar, so the bar is here, this is the bar, in the rest frame of the bar. If the stars are behind in this region here, they gain angular momentum from the torques. And so they can, and if they gain angular momentum, in principle, now the idea is that they could reach the solar vicinity. And the same should happen, because this is, the bar would be like a torquing elongated structure with 180 symmetry. The same should happen in this region here. Now for the stars that are ahead of the bar, which is not the case of the sun, because the sun is behind, for the stars that are in a location here, this location is actually at the edge of the bar, more or less where the inner ultraharmonics are. So if they are ahead, the stars are actually ahead of the bar, they can push backward by the bar. And so they lose angular momentum. So let's see if this some way is what's going on, or at least if we can get an idea. So these are now again, I took now a patch, which is this patch here, a patch located here, it's in front of the sun, 180 degrees. And you can see they, again, so it's exactly the twin of Hercules. So it's vibrating around the other Lagrangian point, which is a stable point, and again reaching the solar radius at that point, because the sun would be on the opposite part. So this behaves similarly to that. Now let's take another patch, which is like the blue patch before. So these are a patch of stars 90 degrees from the sun, so in the azimuth. So those are the ones that are eventually not gaining angular momentum. And indeed, they are absolutely not, so they're not rotating on, so they're not trapped around any Lagrangian point, they're not vibrating, so they're actually dispersed. So this seems to work. Now, if this is true, this means that the stars are not resonant. And indeed, I always had a hard time in proving that they are in resonance, because these are the relations. So now we go back now to the frequencies we introduced with the angle action variables. So these are now the frequencies. So this is the omega pattern, the frequency of the bar, sorry, the omega pattern of the bar, pattern speed of the bar, minus the omega phi of the stars, as a function of the radial frequency. So the green line here, this is for the Lindbland resonances. So for the inner Lindbland resonances, this is the expected linear relation, which is this one. There's a specific linear relation between frequencies if the stars are in resonance with the bar or the spiral arms. If you know the pattern speed of the bar of the spiral arms, you can actually, and if you can compute the frequency of the stars, you can know if they are in relation or not. But these are the Hercules stars. So they are always, so this is basically the Lindbland resonance, and for n equal 2 for the bar, these are the ultraharmonics. This is the inner ultraharmonics for a spiral arm, n equal 4, and this is the Lindbland resonances for the spiral arms equal 4. So you see the stars that are in my simulations as tagged as Hercules, they do not satisfy any of these relations. So, and I think it's not so surprising because they don't have closed orbits, but they have loops orbits. So I think I will conclude from this preliminary work that they are not actually in resonance. So this means that we are not seeing a resonance in the solar vicinity for Hercules, according to this work. Which are the open questions that I still have? So I showed you one explanation, a possible explanation for a slow rotating bar, a long bar for the Milky Way for the Hercules stream. Of course, there are many other moving groups that now we can identify not only in the velocity space, but also in the action space. Where do they come from? They have different properties. So, you know, they definitely will have a different origin. So do they have a dynamical origin or not? But for me, so the similar analysis could be extended to the other moving groups that we know in the solar vicinity and try to understand, you know, maybe if they are resonances or not, in which are resonances or not. But for me, the most important question is try to get now if there is a link between these moving groups with dynamical origin and the star formation. Because going back to again, so it might be that, you know, some of these moving groups have dynamical origin. They don't form in an open cluster. They are not an open cluster formation. However, if there are resonances trap stars, but they can trap also gas. So they can even form, you know, new stars. So because you know, we know that some of the open cluster overlap with the moving groups. It would be interesting to understand if we are seeing, you know, resonances or not, scatter stars, or if we can go to the different location where we are expecting having resonances and finding star formation. In that case, we should find younger star forming there. And so the link, of course, it's very interesting, but it requires gas. So I'm very happy to be here because I can get a chance eventually to engage you in this work. And I think it would be extremely important to have the same simulation with gas added and start, you know, looking into some of these topics. So my summary is just summarizing now the main points. I showed you a self-consistent embodied model with just stars and halo right now of a Milky Way galaxies as we believe it is today. In this model, we identified the origin of this moving group coming from the inner part of the galaxies, as the data would suggest, so with eccentric orbits. The bar has basically the main role here. So I would say that the spiral arms, for sure, they might help, but they are not actually playing a role in for the Hercules stream. And it's really the torque of the bar that could actually be a process, which I'm trying to prove now, to explain the gain of angular momentum of the stars. So these stars would not be actually resonant stars, but they would be just visitors for the solar vicinity coming from the inner part of the galaxy. Some of the validating tests, well, if this theory is correct, this idea is correct, we should go with, I don't know if it would be possible with Gaia, probably not, but anyway, it would be interesting to go 180 degrees you know, opposite to the sun and test the patch over there and see if we have a sibling you know, could have a similar twin for Hercules, because those should be the stars that are actually reaching the solar radius, but they are librating around the opposite Lagrangian point of the bar. And of course, the upcoming data from the coming data from Gaia, but also the SDS-V that will take many more abundances and chemical elements for each star could actually prove. So it would be interesting to see, what is the metallicity of this group of stars, because they are coming from the inner part of the dice and might have actually different metallicity than the background stars. And I think I'll stop here and take your questions. Thank you.
Thank you very much for the great talk. Keeping the time excellently. Are there any questions? Avi?
So, Elena, does the bar also drive the waves in the dark matter? Does it create a core for the dark matter in your simulation? Is the dark matter alive?
Yes, the dark matter is alive, but I haven't really seen the formation of a core.
So it stays roughly the same.
Yes. So yeah, I haven't seen the formation of a core. But it's another important debated topic. If you can create the core with the bar or not, but I don't see it.
Nothing.
So I have a question about your first test of validating this picture. So perhaps, so I'm thinking in the direction of, you said that there are like regions in the galaxy where you can gain or lose angular momentum. And so it sounds like this around the sun, we would only be able to see Hercules stream out to some distance, because at some point we'll get to the region where stars, kind of lost the angular momentum and are no longer kind of producing that lower density. So I was wondering if that would be easier test for Gaia, if you can make a more quantitative prediction of like what's the extent where we can see.
Yes, I think that's a very good point. Yes, definitely. So I haven't explored yet all the torques and how they work, at the corotation with the bar, and but this is something that it would be absolutely interesting to do. So it's a good test actually. Thank you.
And maybe going along in that direction, we happen to live in a particular place where within 200 parsecs of us there's this Hercules stream coming through, but chances are that's not the strongest stream that would be thrown off of this resonance. So maybe looking at the simulation, there'd be other locations in the galaxy that would show a more distinctive.
Yes, absolutely. I totally agree with this. I think this is an excellent point. Yes, I only focused on this specific stream for now.
Well, this is the one this is the lamppost we live under.
Yes.
Gaia made a lamp.
Right.
Quite a bit brighter.
Yeah.
Yes?
So when you look at this torque and where angular momentum is gained or lost, that's an instantaneous picture, right? So these stars actually go through many orbits. So sometimes they gain, sometimes they lose. So shouldn't it be better to look at the long term, the secular event, as we do in celestial mechanics? And there, it's orbit average that matters. And so in any given orbit, precisely because the potential is not rotationally symmetric, angular momentum is not conserved. However, that doesn't matter in one orbit, because they generally more or less cancel out. It's over long periods of time they gradually build.
So how many orbits I should look into? Because
I'm not quite sure. I'm not so familiar with this.
Your number of orbits are not my number of orbits.
I'm not quite sure in this context, but I know in celestial mechanics, and what is relevant is the resonant angles. And when you are looking at this, because eccentricity is a vector, it's not just a particular magnitude, and then one need to correlate that. And also these oscillations you see is normal in celestial mechanics because resonant has width, and it's not exactly follow a certain pattern and with certain frequency, so they do modulate. And
I think it's a good insight. I mean, I've seen you have a paper on planets, right?
It's
On
a-
Jovian planets.
Jovian planets.
I have to try to press similar analysis. I haven't done it yet.
But the sun only did 30.
Yeah, but the
orbits in
secular
itself.
but the secular time scale can be shorter, and especially on this type of scale. And whereas the sun and because Jupiter's mass is so much smaller than that of the sun, so it takes a long time to build up. But here you have much larger, much stronger rotation.
Yeah, definitely. Thank you.
Okay, so Elena is anyway visiting here. She's on sabbatical here, so if you have any further questions or want to discuss with her, you can find her in her office in the second floor. And so let's thank Elena again.
Stellar use.